So hi, I ended up changing the title of the talk a little bit into virtualizing simple Linux firmwares. I thought it was a little bit more concise and actually explained a little bit better what the talk was about. So there is the quick question: who the hell am I to stand here and talk about this? My name is Jens. I have worked in cybersecurity now for about 5 or 6 years. I specialize in the side of something that's called binary exploitation and reverse engineering. So Søren here earlier talked about embedded devices and stuff like that, and that I live for that. So I specialize in, if you remember, buffer overflows, heap overflows, kernel exploitation, stuff like that. That's my bread and butter. And I'm also associated with a couple of CTF teams. The one most known is probably Calmonium. I have to talk a little bit about the company that I work for, ICS Range. So basically, we do a bunch of different things. One of them is breaking stuff, and that is the reason why I actually have this talk today. And I want to talk a little bit about why I'm talking about actually virtualizing Linux, simple Linux firmwares. So we had a customer actually come in who wanted us to test a device. And the reason that they wanted to test it is because if it turned out that it looked like that the device had a pretty good security posture, then they were going to buy 200,000 of them. But at that current stage, the only thing that they had of them was a prototype that was for testing purposes only. So they were just testing whether or not it could fit in their infrastructure. So we could get that prototype, but we were not allowed to open it up. So all this cool hardware hacking stuff that Søren just showed you guys, yeah, you weren't allowed to do any of that, unfortunately. So in that case, we came to a question, which was, is there a way that we can set up some kind of virtualized environment of a firmware, of a device where we have a firmware for security research purposes, for testing? Because a lot of the times we are actually interested in testing, protocol implementations and stuff like this. And in that case, we kind of want an environment where we don't have to be scared that we break the device, and then we will have to wait weeks to actually be able to restore it. And this would actually fix it. So, of course, you lose some of the cool stuff if you virtualize something. You lose some of the hardware component things. So, for example, if I virtualize something with a Wi-Fi board on it, there's a very good likelihood that I lose the whole Wi-Fi component if I'm virtualizing it. You can do a little bit with QEMU and stuff like that, and you can kind of get some part, but you will lose some hardware parts as attack surfaces. You will also lose like anything that is side channel attacks. There are a lot of different hardware side channel attacks, like you can read off AES encryption keys from electromagnetic waves and stuff. You will lose that. It just disappears. So there are some cons with doing something like this, but if you are in a constrained environment where you are not allowed to open the device anyways, something like this could be useful. So I have to talk about also why, maybe, just very quickly, what is the difference and why would you even bother with this? So in IT, actually, when you learn to test and pen test and create all of these exploits or build exploits from the bottom up, you usually learn that, what you want to do is you want to duplicate the environment that you are attacking as much as possible. And whenever your environment deviates from the environment that you're attacking, then you want to go in and fix your environment. Okay, it needs to behave like this instead, so I'll make it behave like this instead, and then you continue your research. Now, we don't really have, or I hadn't had the actual opportunity to actually do that with OT devices a lot, or embedded devices a lot, because it's like, well, I can't just download it online, download the source code, and just run it on my Ubuntu server or something like that. That's not how it works. I have the device physically, but I don't necessarily have a firmware for it. And that would just be a lot easier to test. So duplication is one big thing. Another thing is like a lot of the times they want us to test in a lab first. It would be really nice if we don't have to physically go out into a lab that is set up exactly like their actual infrastructure, and we instead would be able to just kind of mimic the communications and then figure out how are the protocol implementations, stuff like that. So with that out of the way, I talked about them last year as well, but I will mention them very quickly again. I will be using the W2150A as a case study. This thing is end of life and it is dead. You're not supposed to be using it. If you are, get rid of it. They have, after I did the talk last year, it has become end of life. So you probably don't want to run it. So. But the reason I actually use it as a case study is because I have the firmware for it and I've talked about it before. And I like it because I have a 0 day on it and I can do a couple of different things. Well, I have more than one 0 day on it, but. So what I wanted to try and do is emulate the environment of this thing as much as possible. And because I could spawn a shell on the real thing, then I could see what the actual differences are between the one that I'm going in and emulating and the real thing. I am not the first one to talk about emulation of firmware. I'm probably just one of the first people that are going to talk about it as in depth as I am, because I want to mimic kernel versions. And the reason that I want to use the same kernel versions is because memory layout actually differs between kernel version 2.6 and 4, for example, how it actually layouts the memory in user space. And that matters for me, because I usually find a lot of memory corruption bugs, and it actually matters to me, for example, if it places one shared object right after the next one or not. So that is the main reason. If you are interested in knowing how you can just get far enough that you can get something working and looking like the real thing, there is a really, really good blog post by Azaria Labs that is called Emulating ARM Firmware, and it is a very, very good way of getting started with something like this. So first, let's get the Linux kernel information, because that's the first thing we need to kind of figure out. So we can't use the kernel that's in the Linux firmware just as is. And the reason we can't use it just as is because there's a lot of flags that have been set that, for example, might, one, close the console, or two, it has like a built-in init ramfs, which is an init system inside of it. So there's a lot of things that you can't just use the actual kernel that is inside the firmware directly. You can byte patch it into working if you want to byte patch enough. This one specifically would be a pain because it doesn't have serial drivers for QEMU then, but it is possible. So I wanted to extract as much stuff from this as possible. I find out that this thing is running Linux kernel 2.6.31. That means that the kernel for this was new when I was 11 years old. So yeah. But yeah, so I find the kernel, it has an embedded init RAM file system, and I'm able to get that out, and I'm also able to get the make config file out for the Linux kernel that they used, which means that I can actually duplicate the environment very, very closely because I actually have their kernel config file. It's only possible to get the kernel config file out if they have compiled it with a specific flag that allows you to. So you're not always going to be able to find this, but sometimes you get lucky. Now, they are using an old kernel, and I could just stand here and tell you, let's just compile an old Linux kernel. But here's the thing. That is, if I have to be very nice about it, that is a pain. So if you've never tried to, cross-compiling Linux kernels is a very, very well-documented process. It's very, very, it's done to death by people online, and it's a thing that you can easily find a guide somewhere that allows you to cross-compile the kernel. The problem is that the older the kernel is, the worse the resources for it is, how you compile it, because not nearly as many people were using Linux back then. This is from this kernel version is from 2009, which makes it a decade and a half old. you need to use GCC version 4 to be able to compile it, because that is the newest version of GCC that it actually supports. Yes, I said newest. We are on GCC version 13 now. So we, but the good part is that we can still find the Linux kernel source online, because the Linux kernel archives exist. So we can grab the source, and we can get actually a Linaro toolchain version for it, because Linaro actually has a cross-compile ARM toolchain laying around which uses GCC version 4. There are some other considerations that you also need to think, because like then you have the cross-compile toolchain, and then you find out that Perl was also patched. Yes, Perl, that one. It has had like syntactically different things that has changed over the years in how you script in it, and because of that, your Perl out of the box is going to throw an error when you're trying to cross-compile a Linux kernel. In this case, it's actually very easy, because it hasn't changed that much. You just go on into one file in a Linux kernel code, and that's called timeconst.pl, and then you change this line. So you basically just delete a couple characters where it says defined, and then you're fine. When I'm doing this also, I want it to run in QEMU, so there are some other considerations, and that is the board is not going to be the exact same. I mostly want the kernel to be as close as possible, but the board is not going to be the same, and that is the firmware that I'm trying to cross-compile or want to emulate is an MX32 board, and QEMU just doesn't have support for it. So I usually say, as a general rule of thumb, versatile AB and versatile PB are great for anything that is some kind of 32-bit ARM. That uses an older version of a CPU, and anything that is newer, so anything that has the NXP logo on it or has Yocto written anywhere, you want to use the IMX6 or IMX7 board, depending on what the kernel config file says. Cool. He talked about the boot process a little bit earlier. I'm just going to go a little bit more in depth for how it works for Linux specifically. So basically, the way that it works is that we start off by booting into the Linux kernel. So I'm completely skipping the U-boot process or the bootloader process. I just expect that you are just jump right into the boot process of Linux here. It then checks, is the kernel compressed? Because it actually has inline compression of itself. If it is, then it uncompresses it, and then it starts booting the kernel from the address that it has been specified in the firmware. After that, once it starts booting the kernel, it loads any drivers that are necessary, so like SCSI drivers, stuff like that, and then it goes in and then it checks if it has an init RAM file system. This is a temporary file system, very volatile, and that is why it's called a RAM file system. It is just think of it like a stager. Like it walks in and then it just like mounts everything that needs to be mounted and makes everything look cute, and then it jumps into the actual operating system, or like actually mounts the right things and then jumps into the actual init process and actually does everything that it's supposed to. And of course, if a custom init file is specified, then it uses the custom init file. You can specify that on the kernel arguments, or it uses /init as per default. Then QEMU is the one that we're going to be using to emulate this. So now we have a compiled firmware, then we also need something to be able to boot it, because to check whether it's working, because we are working with ARM. So I really like QEMU. It's a very good emulation framework. And the main reason that we targeted, in this case, versatile PB or versatile AB boards for this is because we will be using QEMU. If you find any better emulation pieces of software or general purpose emulation software, let me know. I tried to find something for the MX32 board, but I found nothing, unfortunately. So we mainly just want the CPU architecture to be supported, and we want the Linux kernel version to be the same. Then lastly, we need to put in the file system because we just have the kernel now. We need the file system to actually be working too. So there are a bunch of different ways to do this, and there are a bunch of different ways to do this depending on how much memory you have, what type of system you actually want to end up with, because we're doing this for security research purposes. We are not going to have the exact same file system because we want to put in stuff like debuggers, or we want to be able to put in custom software that does custom things because we need to, like, for example, remove an error message because it doesn't actually happen, or some things like that. So if you want any changes that you do to the file system, you want them to stick after boot, then I can highly recommend actually implementing a proper init RAM file system like their own, and then actually mounting a disk that you have attached to it, or a virtual disk that you have attached to it, which then goes in and actually has the real file system and everything on it. If you don't want to do that, and you just need it to not stick with the changes every single time, then I would highly recommend just putting everything into the init RAMFS and then run with that, because then every single time that you reboot the system, it's going to the file system is immutable, so it's just going to go back to basics. We will be using, by the way, for the rest of this talk, I'm showing it for the init RAM file system, how we go on from here. So once we actually just put in the init RAM file system and we ask it to boot, we start actually getting output, and we start actually booting into this firmware that we're trying to emulate. So we're actually a lot of the way there already. In this case, I think here I took the SquashFS and then I outpacked it, and it used overlays, and I kind of just smacked everything into the init RAMFS instead. And at the bottom here, there's a command if you want an idea of how you boot something with QEMU. But yeah, other than that, we can see that we are actually able to boot. There is a couple things that we want to fix with the boot process before we continue. One of them is that we're getting the same error all the time at the bottom there that says /dev/tty m32 open fail. In this case, I know that the tty m32 in this case is actually the serial console that it wants to attach to, the one that is at the end of it, and it has no purpose for any of the tests that I'm going to be doing. So I actually end up writing a little bit of a shared object in C, and just go in and basically preload it to remove this error message. There's also other small errors. I don't know how I actually do a pointer on this thing. This one? Okay. So there are, if you see here, it says like, hey, /user/bin IP conf check and conflict IP check. It can't find those. In that case, it's just because there are a couple symlinks are missing. So if we fix that in our init RAMFS, it works fine after that. Cool. Now we have something that can emulate it and actually kind of works, but we're still standing in a problem where we need GDB server on the target. We need to be able to actually debug, or in this case, I really want GDB server because then I can actually debug inside the memory of each process on the thing, and it's also really useful for what's called dynamic analysis for research purposes. So the problem is that the Linaro toolchain refuses to cross-compile GDB server statically, so I end up basically looking at build-root. This is where it takes a weird turn, because when you're dealing with software that's this old, it doesn't compile properly on newer versions. So GCC decided in their infinite wisdom, or GNU decided in their infinite wisdom, that whenever they make a GCC version or a compiler version, they will make sure that they are forwards compatible but not backwards compatible. So what does that mean? That means that if I use GCC version 5, I can compile GCC version 8, 10, 11, 12, 13. If I use GCC version 11, 12, 13, I cannot compile GCC version 4. So I cannot compile backwards, I can only compile forwards. That's kind of a problem, because we need the old compilation toolchain and older GDB server, because otherwise it's using instructions that the CPU doesn't know. So the problem is that build-root kind of fails trying to compile the actual compilation tool chain. So I end up having to figure out how to go back to an older tool chain, which is Debian 6. And then it ends up being a little bit more complicated because Debian 6 has a bunch of problems, because Debian 6 is also very old. So none of the apt repos work, and there's just nothing that actually works in this thing. You have to remove signing, and then I had to manually patch something that's called libcdev, because it also didn't work. And we actually end up finally, in the end, after struggling with this thing, and frankly struggling with this issue for hours, trying to make sure that I can actually get my debugger on it, I finally stand in a situation where I have GDB server version 7.4 running on the target. And that means that now we can get to the last part, which is going in and trying to change parts of the boot process so we can go in and attach debuggers to everything. We can go in and change parts of the init process to make sure that it spawns things with debuggers that we want it to spawn with debuggers. We can use GDB locally, then connect up to GDB server on it. We can, but also because we made the cross-compilation tool chain with build-root, we're standing in a situation where we can also just compile other software for it. Oh, this virtualized device didn't actually arrive with SSH. Not a problem, we just compile SSH for it. We have a tool chain that is able to do so. So we can make changes to files, we can add new files, we can add new software to it. So if there's something that we're missing to do our research, then we can do so. And that actually makes our lives a lot easier. So it's not really a thing if I don't show you the thing actually running, because I can stand here and say all these smart things and then it doesn't matter. So this is a short demo of it. So here we're spawning it, and this is a W2150A. And this is also what the boot process would look like on the W2150A itself. There are some extra things, like debugging things, that I've added myself here, but now I'm actually basically spawning the Moxa DSU. This is a proprietary tool by Moxa created to find these W2150As, or Moxa devices in general, and it just works how it's supposed to. So I can open the console, it can actually find the Moxa device, and it sees it as a Moxa device, and I can actually log in to the interface, and I can change whatever the hell I want on the, on the web interface. But I can also go into Telnet, because all of the other, all of the other ways of interacting with the system is working as intended, because I'm not just mimicking one part of the firmware, I'm mimicking the whole thing. And that allows me to spawn the real Telnet sessions and everything. So, key takeaways from this, and what did we learn from this? Doing full systems emulation is time-consuming. And the older the firmware is for these things, the worse it is. We ended up also, we have virtualized multiple firmware since this for security research purposes. And what I can say is it's a lot easier the newer it gets, but you just end up having other weird issues. There are always some issues with making these things run that needs to be fixed. And these are hour-long, week-long, month-long projects to actually get them up and running. However, once you have managed to create old build tool chains that help you actually compile a lot of this software and getting this stuff done correctly the first time, if you keep them, then a lot of the issues that you will run into will be the same. And if you have fixed these issues once, and then you have managed to actually create a tool chain or things that can help you in the future, then you can do it faster in secondary iterations. So the first 5 times takes forever, but then the next 6 times takes maybe 45 minutes. So it's very heavy in the beginning, a very time-consuming process in the beginning, but once you get further and further into it and you do it more and more often and you have more experience with it, then these issues are all the same that you get. Statily cross-compiling GDB server versions suck, mainly. I had 4 slides in this presentation that didn't need to be here, just because I needed to cross-compile GDB server. So then we can talk about how maybe that should not be a problem. So GNU, why is that a problem? That should not be a problem. But also with almost full system emulation, it's possible to set up environments where memory-wise they actually mimic the real operating system very closely. So I actually tried, I have a memory corruption bug on the W2150A, which gives me unauthenticated RCE, which I presented here last year. And I, of course, tested it on it to see whether or not it worked, because then the memory layout is correct if it does. And the answer was yes. So I actually had something that was so close memory-wise that this very specific memory corruption bug actually was able to be exploited in the correct way from the system. So but this will allow you to also, if you know you have a buffer overflow, this will allow you to actually debug your buffer overflow exploit before even being able to spawn a shell. Because in the original talk, if anybody remembers, we actually had to find a secondary vulnerability that allowed us to install a what's it called, debug toolchain on it. So and I think that's all I have. So thank you.